Okay. Thanks everyone for coming to the CI Engineering Brown Bag today. Our speaker today is Frank Wuerthwein from UC San Diego. Frank wears a variety of hats in a variety of circumstances. He's a physicist, knows a lot about computing, a bunch of other things as well. Today he's going to be talking to us about the Open Science Grid and high throughput computing. The title of the talk is Advancing Science Through High Throughput Computing on the Open Science Grid. So Frank, take it away.
Thank you. Can you hear me well?
Yeah, you're coming through great.
Okay, so as advertised, I'm going to talk about advancing open science through distributed high throughput computing. And so I want to start by parsing my title a little bit and acknowledging upfront that the purpose of this talk, in my mind, is to give people a sense of what Open Science Grid is trying to accomplish, who it is trying to accomplish this for, and what is the methodology that we're using. But if you wanted to know anything that is resembling technical detail, I'm not going to get into it, because that in its own right would divert me in a nanosecond and probably take a lot longer talk than this. And so my hope with this talk is that this is sufficiently interesting to people that you can then engage with me or the help email that I have on my last slide afterwards to find out more, because you like what you've seen. Okay, so let's parse the title of this talk. What do I mean by advancing open science? So what I mean by open science is literally anything that is non-restricted, irrespective of discipline. Meaning anything that isn't HIPAA, FISMA, or alike. Anything that allows for data sharing, where data may be public, may be private. So data privacy is full within scope, but not the kind of regulated data that you find in HIPAA or FISMA. In addition, we want to advance open science for the maximum possible dynamic range of science, groups and institutions. This ranges from individual undergrads to international collaborations with thousands of members. It also is, in terms of institutions, it goes from small colleges, museums, zoos, to national scale centers of open science, meaning that you in national labs are as involved here or as much relevant as the American Museum of Natural History. Or there is a couple of different zoos that we work with. And we want to advance this entire spectrum. In order to be able to advance the entire spectrum, requires us to have a diversified portfolio of services. And I'm going to talk a little bit about that diversified portfolio of services and a lot about the driving vision behind it and how we decide what services make it into the portfolio and not into the portfolio, and why we pick certain things. And you should ask me, you should interrupt me at any time when you have a question, and then we'll deal with it as it comes. Then to give you a sense of open, here is the accounting by field of science. Where this comes from is I take the wall-time consumption accounting within the last, I can't remember whether it was 3 months or 6 months or even a year, and then look by field of science, and then just do a screen grab of those fields of science. What you see here is declarations that people make themselves. In other words, this is just a string that people can fill in when they register for use of OSG. And the individuals who signed up or the organizations who signed up have chosen to declare themselves via these strings. And you can easily see that there's all kinds of stuff there, including zoology, there's economics in there, there's different kind of engineering, biology of various types, lots of different stuff. And fundamentally, there is no restriction of any way, shape, or form. It's not funding agency restricted. It's not restricted to anything's possible. And science is interpreted liberally, meaning humanities, digital humanities, that's all fair game. Here's the same for accounting by organization. And again, people self-declare their organization. You can easily find here that people have some existential crisis of some sorts, like the University of California, San Diego, where I'm from, shows up here under 3, 4, 5 different names, because apparently we can't agree on how we call ourselves. And that's simply because we do not restrict how people consider their organizations. You will find here organizations that are brick and mortar, but you can also find this thing here, dark side, which is a particle physics experiment. So some people think of themselves not as belonging to an organization that is brick and mortar, but to an organization that is a multi-institutional entity. DOSA is a similar kind of thing, and there's a bunch of others across. But most of these are brick and mortar institutions. There is the American Museum of Natural History down here, as I had promised. And if you then try to ask yourself, how do you make sense out of this mess of that very open, very diverse, very broad set of people? We think of them as classified into 4 different types of community, types of groups. And we think of these 4 different types because we've identified that different people require us to do different things for them, and that they roughly fall into these 4 types of entities. And so the first is just individual researchers. We provide individual researchers services that are basically end-to-end. It starts with giving them an account and teaching them how to use that account, and then allowing them to import their data, et cetera, et cetera, et cetera. And then you compute on their data. So in a way, we are functioning like a campus research support organization, except that our researchers that we serve are from everywhere. And it's for the people who don't know that they have a campus research support organizations, or they don't like working with them. And that's the people who come directly to us. The next kind of category is then the campus research support organizations. We're trying to work with these organizations, especially the facilitators or the people who work with scientists, researchers. We teach them, we teach the facilitators how to teach the researchers about OSG and how one does high throughput computing. And we work with IT organizations and support services for these OT organizations in order to integrate them with OSG. If you're supporting an IT organization at some campus, you would fall into that kind of category, and there's lots of different things that we do. We've even done, at one point, we've been approached by a university campus IT organization that had lost a lot of personnel, and they've literally ended up paying us to reestablish themselves on the map, to literally do everything, all the way from advising them on what batch system to choose, in helping them install that batch system, basically get them started over because they had lost so much personnel and wanted a jump start. And we're basically willing to do whatever it takes to get science done and work with campus research IT organizations in accomplishing that. The third type of category is anything that is not bound by a single institution. So if you read this from the top to the bottom, you realize that the scale increases, and therefore, in some sense, the complexity increases. When you have multi-institutional teams, you don't have line management anymore. And therefore, you have to develop collaborative things where people can federate and can work together. And we provide the glue, the plumbing, the whatever it takes to allow groups that span institutions to be functional together on resources they can contribute to each other. And this is mostly large astronomy, or mid-size, I should say, mid-size astronomy and physics experiments, meaning instruments. It's driven by instruments largely. But fundamentally, if you had a collaboration between the University of Kansas and the University of Nebraska or whatever, that would be just as good a multi-institutional science team if they want to study corn together, and I'm making this up as I speak, then that would fall into this category, and we'd be available to help those kinds of multi-institutional groups in order to share resources, et cetera, et cetera. And it'll become more clear when I go into detailed examples. And then the last one is the 4 big science projects that we can actually enumerate because they're so large as global enterprises and have such IT teams or CI teams themselves that they are sort of a special beast in their own right. And therefore, we think of them as separate from the others because we tend to work with them very differently than anybody else. And there are Atlas, CMS, LIGO, and IceCube. And this is just the 4 big ones right now that we work with. It's entirely possible that next year when I talk, it would be 5 big ones or 6 big ones. It basically, this is bound to grow at some level, at some point. Any questions so far? We're good? Then let me talk about the second part of the title, distributed high throughput computing. What do I mean by that? And first of all, let me introduce my acronym. dHTC stands for distributed high throughput computing. And the challenge in successful dHTC is sort of twofold. That it's one, to separate a big computing problem in many individually schedulable small problems that are independent to the extent that they don't have to happen in concurrently. They can happen concurrently sometimes. Sometimes they depend on each other in a sequential workflow, but they don't have to happen. There's no requirement for them to be concurrent. That's basically a challenge for if a science workflow can be decomposed into something that is individually schedulable on a per node basis into many pieces that each are individually schedulable, then we can apply dHTC as a paradigm to solve the problem. The second challenge is that if you want to be successful in a distributed high throughput computing environment of the kind that OSG provides, then you want to minimize the requirements in order to maximize the raw capacity that you can effectively use. What's behind this is that our basic fundamental principle is that truth in advertising and then match advertisements to each other. So if you have somebody wants something, somebody else is willing to give something, we're there to provide the plumbing to bring the two together and execute their collaboration, so to speak. And if you want to maximize the raw capacity that you can effectively use, then you want to be reasonable in your requirements and target so that you can target the largest possible envelope of people who are willing to work and give stuff away, basically. That's what is behind this point. And we can teach people what's currently available in bulk, so to speak, and therefore can work with people on requirements that they have and readjust. A lot of this has to do with memory requirements, I/O requirements, data requirements, and often these two problems are very interrelated, and we figure it out, help you figure it out, and how to make this work. We then teach researchers how to meet these challenges, and we take many small problems, schedule their successful execution, and we allow people to curate and publish their software and data, and at runtime, we guarantee that we deliver it to you. And I like to call this ingenious parallelism because it a priori scales indefinitely. If you can arrange a scientific computing problem in this manner, then you have, in principle, only one thing stopping you from scaling, and that's money. possibly infrastructure. I'll talk more about where the practical limits are in a slide later. So I call this ingenious parallelism because it is incredibly powerful. I want to make sure that everybody understands that GPU computing is part of dHTC. That wasn't always that way. We've learned within the last, I think, probably 3-4 years, from small beginnings to now large-scale production, that GPUs are just no different. In fact, the standard node deployment that we have, where we have GPUs, is 8 GPUs per node. So anything until 8-way parallel of GPU use is possible on OSG. We have a large variety of different GPUs, basically anything you can imagine, from gaming GPUs to V100s are accessible via OSG. And so again, if your requirements are minimal, in other words, if you can work with single precision gaming GPUs, you're going to find a lot more on OSG than if you require V100s. And the other thing that is, you see here as a beginning of this, the peak day is 2,000 GPUs. As you can see, this is one day on 3, 8, 9, 10, 11, 12, I think. And the other thing that you see here is among the places that IceCube uses, a lot of them are IceCube collaborators. This is a theme that is very generic, a pattern, so to speak, of OSG. We help organizations to integrate the resources that their collaborators own. And that makes it a powerful way of working with OSG, especially if you have collaborators. And I'll get more into this later. Then I want to briefly mention that apparently what we do is recognized by the national academies. There's this report out that says many fields today rely on high throughput computing for discovery. Then there's the obvious shoulder clapping. There is 2 discoveries that in the last 10 years got Nobel Prizes. And this is the Higgs discovery at the LHC, which gave the Nobel Prize to the 2 theorists that are still alive and predicted the Higgs. And then the gravitational wave discovery by LIGO, and that gave the people who initiated that project and ran it to completion the Nobel Prize. And both of these are customers, meaning you heard already LIGO and the LHC are customers. And both the data analysis that led to these Nobel Prizes was in the Higgs case entirely done on OSG compatible infrastructure, and in the LIGO case partially done on OSG infrastructure. I wanted to impress upon you again that distributed high throughput computing is a very special paradigm of computing, because as a computing paradigm, it scales by definition perfectly. When a researcher understands how to partition their workflow, they can scale out dramatically, pretty much instantaneously. And this scale out is very easy. This is fundamentally very, very different than MPI scaling out or tightly coupled, because there you have every time you're trying to scale out, you have fundamental issues of concurrency. In dHTC, there are no concurrency issues. Therefore, you can run on any computer that you have access to. And it's OSG's problem to provide the plumbing to grow scale. Again, I call this ingenious parallelism. I wanted to give you one example application of a single researcher, and I picked this particular one because it shows a pattern, again, that is a very useful pattern and a very powerful and common pattern across OSG. And that is that the guy here, J.J. Riethoven, Jean-Jacques, if I remember correctly, combines campus resources at his home institution with OSG resources and makes heavy use of both data and compute federations that I will be talking about afterwards. In other words, he's got data, he needs to compute, and some of his computing happens to be only local at his home institution, and some of it is sufficiently flexible that it can scale out elastically into the entirety of OSG. And that kind of arrangement is a very powerful way of thinking about how do I make best use of OSG. And so here's what he does. He's part of an bioinformatics outfit, and their goal is to understand the role of diet and microbes in the role of microbes and diet in disease. And they're therefore trying to analyze the composition of your gut microbiome and the impact that it has, or the correlation that it has with health or lack of health. In other words, different kinds of unhealthy conditions that a body may be in, and what role does diet play, what role do microbes play in that, in either getting out of that condition or, in other words, get healthy again. And so there is a whole lot of gibberish that I barely understand on this slide because I'm not a bioinformaticist. The thing that I wanted to highlight is that, do you see when I use my my pointer on my slides?
Yep, we can see your mouse pointer.
Okay, so what I want to highlight is these 5 steps that his approach includes. And he has an initial database that he needs to extract data from. That he does entirely locally. HTC is the Holland Computer Center at University of Nebraska-Lincoln. And so there's a step where he extracts information out of a database that he does local. Then he determines, there's a heavy compute step that uses a data set over and over and over. And that he uses the Data and Compute Federations in OSG. And so he basically elastically scales out from HTC into OSG. Then he comes back and does some simulations locally. And then he goes back out, elastically scaling out, to determine a protocol interface with the highest binding energy. And finally, he brings it all together and does the final analysis back at home. And I'm assuming that step 3 he does in Nebraska because it's possibly heavily coupled. There may be some MPI kind of stuff in the middle. And then the last one, probably because it's easy to do, it doesn't require a whole lot of computing. And so he keeps that at home again. And this is sort of a pattern that we see in a number of scientists. And it effectively uses OSG as an elastic scale-out engine. And I'll talk more about this in later slides. One slide on the aside on limits on scalability. If you ask yourself, how large can you fundamentally scale with this kind of thing, given that the application does not provide any limit? It is ultimately the scalability of the middleware we use. And what I'm showing here is the scalability of Condor as a function of releases as measured in collaboration between the Condor team and the OSG team. And you can see that I think this spans roughly a 10-year horizon, maybe even a 15-year timeline. I'm not 100% sure anymore. And the most recent scalability of the most recent version is 200,000 startees effectively in a single Condor pool. Now, what does that mean? What's that question?
Well, just a comment. That's 2 orders of magnitude. That's not bad.
Yeah, and trust me, this took a lot of work. It's been the scalability stuff started between CMS and Condor in more than 10 years ago, and therefore I'm guessing that this first point down here is actually 10, 15 years ago. It was around, we started this game in around 2007-ish or so, or 2006, in that neighborhood. And the most recent one is, I think, from last year, within the last year. And this is not a linear timeline. Basically, every time that somebody needs another step up, we go at it again. And there's many, many changes that were made to the basic Condor software. Now, what does it mean? This means you could run in a single batch system 200,000 virtual machines. If you then ask yourself, what's a virtual machine today? The ones that I'm just buying off the shelf is a dual 20-core system. 200,000 of those would be 8 million CPU cores. Of course, we don't have that kind of a scale, but that's in theory what you could do. Similarly, we deploy 8 GPU systems these days. I just bought one and bought 3 of those. There are 8 28 Ti's from NVIDIA, because they're sort of the right thing between cheap and powerful. And so if you took 200 KVMs, then you could have 1.6 million GPUs. I think the largest supercomputer in the world has something like 27,000 GPUs, if I remember correctly, in that neighborhood. So these kinds of scaling are just exorbitant. And literally we're literally limited not by software really or application. We're limited by how large a system we can integrate. How many people are willing to play? And that's what I'm trying to impress upon you. Join us, play with us. OSG's goal is to grow effective capacity while growing the research community that can benefit from this effective capacity via dHTC. That's basically the most important message I'm delivering here in this talk. This one sentence. Now let's talk a little bit about what's our strategy. What's our strategy for growth? And I will use the word effective capacity in contrast to raw capacity, because the way I think about it is that effective capacity is what I deliver to the end user, to the scientists, to the researchers. And all of the plumbing that we do and turns raw capacity into effective capacity. So how do we grow effective capacity? We've been around the bush a few times. OSG was originally formed in 2004, so that's 15 years ago. We were originally formed as a software-only entity, meaning we integrated a software stack that we then provided a delivery mechanism, and people had to install it and instantiate services via that software stack. And that's all we did. We provided an integrated, tested software stack. We found the hard way that this is way too high a bar to jump for anybody other than the LHC community, pretty much. And so over the years, we understood that if you wanted to grow capacity, grow effective capacity, you have to do a lot more than provide just an RPM. And so today we offer to operate services to the groups we serve, to those 4 groups types of groups that I've mentioned earlier, in order to minimize the threshold to entry for everybody. That means we run basically anything that we offer in terms of software for you to install, we also operate ourselves. That has 2 benefits. A, we eat our own dog food, and B, we can negotiate with anybody who comes the exact position that what should we operate for you, and what are you willing to operate yourself, and integrate you into the larger context in a combination and a collaboration where we run some services, you may run some, or we may run all the services. And there is that gets me to my aspirational goal. We have adopted the following aspirational goal: a campus research IT organization should not have to learn anything non-standard in order to have their researcher benefit from OSG or have their resource be available via OSG. Now, that's an aspirational goal because we're not quite there yet. There are some things that we actually still require that are sort of goofy or unusual, that are not standard. But our goal has been over the last few years of reduce the non-standard things, and all of the hard things we've eliminated. And I don't want to go into too much detail here, but if you want to know more detail, just send me an email and we'll talk. Now I'm going to go through some of these services that we provide and give you a high-level understanding of what they are. And first of all, I've already talked that we operate OSG Connect, which is a submission host for individual researcher. You get an account, we teach you how to use OSG, voila, we do everything end to end. That's sort of the simplest way of interacting with OSG. We then have a Compute Federation, and the Compute Federation's purpose is to integrate any and all resources, no matter what modus of operation they have and what kind of access mechanism they offer you. So that means we integrate from a single access point allocations at national supercomputers, your own cluster that is locally at your campus, your collaborators cluster, national shared clusters, and your credit card's capability of purchasing resources in the commercial cloud. We can make all of this appear as a single Condor pool to your researchers. That's the basic premise of our Compute Federation. Any and all ways that a researcher can have access to compute, we make look as one system because we do all the plumbing to integrate it into one. And so then for the kind of Compute Federation that we have, there's about, OSG federates about 100 clusters worldwide. It's a little tricky to count because we integrate clusters of all kinds for all kinds of purposes. The dots that you see here are clusters that have deployed or are accessible via the OSG compute element. However, there are plenty of clusters, especially outside the US. It's about, we integrate in our meta scheduler 110 CEs inside the US that are deployed, or CEs that are deployed by the OSG software stack, and we integrate another 300 and some globally that use other software than OSGs. In some cases, we integrate clusters that don't operate any CEs. We go there via SSH. So we're basically willing to do whatever it takes to, within reason, to integrate a cluster for a community. And if you want a cluster multi-community served, we provide the means to do so by operating a compute element for you if you don't want to operate it yourself. At the same time as we federate all of this, the number one principle in OSG is owner's rule. We live in a capitalist society. Whoever owns resources, they determine policy of use. All policy is local. Many owners allow opportunistic use of spare capacity. That's the most common policy we see. But many also allow only dedicated use to up to a certain max for certain stakeholders. We have a lot of clusters that are only for the LHC, only for LIGO, only for IceCube, only for Xenon 1 ton, or Xenon 1 ton has a certain amount, and then LIGO has a certain amount, and Atlas has a certain amount, but nobody else. So, and we're willing to do whatever it takes. In aggregate, the OSG compute element deployed infrastructure is about 200,000 Intel x86 cores used by 400 projects across 36 fields of science. Then that gets me to the Data Federation services. That's fairly new. I think people have probably heard of the Compute Federation, maybe not in exactly the words that I described it here, but you've probably heard of it. The Data Federation is much more recent. We have built something that is very similar in concept to the Compute Federation, in that anybody can join it with their data or their disk space, and we can publish your data into our federated namespace. We can make your data public to only the people that you want them to be public to. And we also do eat our own dog food, meaning we have some that we operate ourselves. And then we have caches deployed in the US and one cache deployed in Europe, and which I'll get into in a moment, in order to hide access latencies and reduce network traffic. So the cache deployment inside the Data Federation is effectively in order to make this work better, whereas the origins is to grow the total data available to the community that is served by the Federation. In addition, we have a policy-based data placement and service that is built around something that the LHC uses. It's called Ruscio, and I won't go into detail of why that exists in addition, but think of it as if you wanted to have a content delivery network that the Data Federation effectively is, you have a lot of your data on tape, you first have to have some kind of mechanism to get it from tape into the content delivery network, and that is a poly-based data placement. And so somewhere on top of the Data Federation, you can put a policy-based data placement in order to get that kind of functionality. in the end, we've created the illusion of a read-only global file system for all of open science that anybody can join with their data. Any questions? We're good? Then let me show you a little bit of what's deployed.
Actually, sorry, Frank. I had one. I mean, I was going to save it to the end, but since you asked, for the Data Federation piece in particular, I have a lot of interest in this right now, and I know that several others in the community do as well. In particular, there's a bunch of data that is stored in community data portals. I'd be interested in your thoughts about how we could add those data portals, maybe for optical astronomy, or sky catalogs, or the Earth System Grid Federation for climate science data and climate model output data. There's a bunch of these. How do we integrate them into this federation?
So the way that we do it let me talk about how it's done right now. And this is the list of stakeholders that have done it. So we have 6 origins. This is what we call a data origin. And if we're effectively able to, if you have your data in a normal file system, organized via typical file system semantics, then we can export that file system that you're running as your production file system to host that data, and make that as an origin of the federation. And I'm willing to work with you on making it such that we operate the service that is the origin service infrastructure, and on a piece of hardware that you own. The way that we would swing this is that you have a DTN that is connected to your Science DMZ, and that DTN has the OS installed and then Kubernetes installed. Then you join a Kubernetes cluster of your choosing. We offer you PRP to join to, because that's a collaboration that we have between OSG, a deal between OSG and the Pacific Research Platform, that the Pacific Research Platform is willing to take anybody that OSG brings into its Nautilus Kubernetes Federation. And then you will effectively join the OSG namespace inside the PRP Nautilus Kubernetes Federation cluster. And we then run the origin for you. And that piece of hardware that you have there at your location in your Science DMZ, the DTN that you're giving us, is all it has to do is mount the file system that has the data that you want to export.
Right. And, okay. So it's gluing the file system mount to the.
Yeah, it's gluing the file system to the OSG. Now there is one more step, and that is that in order to make this easy to use for the community, you then we have to have a ingestion into our namespace, so that our namespace actually knows what the files are that exist in your entire file system. And you, for example, you could have a file system only some of which you want to export. And that can be done both hard limited in which you export into the federation, and then it can be soft limited by hiding some of it in terms of not publishing it. So there's a publication step that ends up that makes the files be visible by an LS from anywhere in OSG where CMFS is accessible. And there is a fundamental access mechanism which goes via X-root-D, which is the origin. Does that make sense, Eli?
Yeah, that's great. Thank you. I want to talk more. I mean, I don't want to take up more space here, but there are a couple of things I'd like to talk to you about.
And one of the beauties of this is that the caching infrastructure then isolates the origin from the access. In other words, your origin does not have to be fantastically scalable. It doesn't require that you suddenly have a wonderful file system that you start with that can be hit to the wazoo and not fall over, because almost all the accesses will be to the caches and not to the origin. We basically guarantee that by design, and we actually have accounting for it, and you can see some of that accounting down here, that the caches are the one that gets hit, and the caches are the ones that we operate distributed across the nation. And then that has the effect of limiting the scale requirements on the origins, and it has the effect of limiting data transfer. And so you can see here sort of the reuse characteristics of different parts of the namespace. And depending on community, files were read within the last 60 days 10 to 30,000 times. So different communities have a different use pattern of their data and a different reuse pattern. And we watch the working set, which is basically the sum of unique data that is being accessed. And we watch the total read, which is the total access of this. And the ratio between these two is how often the file on average gets read within a given namespace. And so again, it's really important that the caches have multiple purposes. They hide latency, they reduce network traffic, and they increase scalability. The origins do not have to some all-powerful file systems. We can work with regular file servers, with regular web interfaces. We can work something out of exposing a file system that does not have to be arbitrarily scalable. Fair enough?
Excellent, thank you.
Then I wanted to point that there is one of the 9 caches in Amsterdam, and I'll talk more about that later. Then I want to talk a little bit about the deployment operations model. I've already talked about this a little bit. Basically, I've already told you what comes next. And I want to describe it with the example of network cache DevOps, because that's the cleanest example we have. I think of our network's cache deployments as a layered approach to distributed DevOps responsibility. So OSG has the top 2 layers, and underneath there are other organizations that have responsibility. And so if you go from the bottom up, hardware and OS is the responsibility of whoever owns the hardware. For example, for the caches that Internet 2 provides or GPN provides, they own the hardware, so they are responsible for the hardware and the OS. And they are responsible to install Kubernetes and then join the PRP Federation cluster. Once that's done, there is a possibly distinct, possibly the same organization that is responsible for measuring network performance and debugging network performance. And this is either PRP, TNRP, I2, regionals. We can play this in a variety of different games of who exactly is the entity responsible for the network performance. And it's the usual tools that get deployed here, meaning persona, or moving big files around and measuring time. Then on top of this is the Data Federation service. That's OSG responsibility. And then on top of this is supporting the science applications so that they can know how to use the Data Federation to their advantage. In other words, all of the teaching scientists how to do stuff. That is also OSG's responsibility. And what is important to me is that I think that this is the first time that OSG had this clean a model of operational separation so that people can work together without having to coordinate constantly. Does that make sense? And ultimately, Kubernetes plays a significant role, and therefore Google plays a significant role, because I'm counting on Google to rule the world and teach everybody and their brother and sister how Kubernetes works. And I'm counting on Kubernetes becoming a standard IT function that everybody knows how to do because it's so powerful. And therefore, we've sort of wedded ourselves right now in this model to Kubernetes as a container orchestration model, rather than giving you just RPMs that you then have to install and operate. Any questions? We're good? Then workforce development. We provide a lot of facilitation services. I said this already, so maybe how am I doing time-wise? Yeah, maybe I'll skip through this quickly. We've
got about 12 minutes to go.
There's a lot that we teach people how to do, anything from IT people to end users. and we are especially interested in training the trainers. The last thing I wanted to talk about is revisit the 4 groups. In my mind, I've told you a lot about the first 2, and I've told you a little bit about the last. The last that is probably the most exotic is the middle one. And so I want to talk a little bit more about multi-institutional science teams and largely mid-scale instruments, but I don't want you to think about this too restrictive. If you have a collaboration with another institution and anything that OSG does can be of service, we should talk. Voila, science is a team sport. Here I have given you 4 scientific, 4 scientific collaborations. They do different kinds of science. They have one thing in common, and that is they have a large number of institutions that collaborate on the science that they do. And so the common general pattern is there are many science collaborations with order 10 institutions, and you can see on the previous slide, there's 33 here, there's, I don't know, so maybe a dozen here, there's 20 here, and there's maybe a dozen here. And in each case, it is actually kind of an amusing Venn diagram of instruments on institutions. So there are many science collaborations with order 10 institutions or more. They generally benefit greatly from integrating resources from all their collaborating home institutions. They typically do not have the effort to do that integration themselves. In other words, the total funding for the instrument is not in the $1 billion range, it's in the maybe $10 million range. These are things that don't have the kind of operational budgets that the LHC experiments have, and therefore they depend on help by OSG in order to do the kind of integration that OSG takes for granted, and that LHC takes for granted. And OSG provides them with embedded support. We do a whole lot more for them often than just provide services. We also help them adapt their stuff to services. There's a whole kind of large range of things that we do. And I want to give you some examples. One example is the XENON collaboration and the XENON collaboration operates an instrument in the Gran Sasso in Italy. That's where this sort of a picture is from. So the experiment is in Gran Sasso, Italy. It has its tape archive in Sweden. It has disk storage in 7 locations across Holland, Italy, Israel, France, and the US. They by now have multiple petabytes of data. When I wrote this slide, maybe 9 months ago, it was 20,000 data sets that comprise the petabyte. It's probably by now twice as large, I'm guessing. Maybe 3 times as large, I'm not sure. It has compute sites on EGI and OSG and has NSF HPC allocations. And so OSG took on the integration challenge by embedded technical support, i.e. somebody at Chicago who worked directly with the group in Chicago from XENON 1 ton and the XENON collaboration in order to make this all integrated and work. It's a complicated diagram, which I won't talk about. What I want to talk about is the pie chart of compute contributions. You see in this pie chart that a lot of institutions contributed. You also see that there are certain obvious named institutions that dominate. And those named institutions that dominate have one thing in common. They are collaborators of XENON 1 ton that have MOU commitments to support operations, compute operations for XENON 1 ton. And what OSG has done is combine that and present it to XENON 1 ton as a single batch system, as a single data infrastructure. And that kind of thing is what OSG does very well for these kinds of partners. And you can see there's also an XD allocation by Exceed on Comet that is a significant part of the overall. And so if you have PIs at your institutions that are part of larger organizations like this, then OSG should be an obvious partner for you to work with. Another example, South Pole Telescope. South Pole Telescope is significantly smaller in terms of scale than XENON 1 ton at this point. It's located at the South Pole, so they have to first get their data out of the South Pole. And let me just give you one small example of what we recently did for them. There is a daily satellite data connection and that is archived in Chicago, ultimately. in February, the guys in Chicago noticed that they couldn't get any transfer out of the point where the satellite hits the US. It's called USAP. And you can see here, basically, this is what was happening. And it was flatlining at a very small, pathetic level. They then got in touch, the Chicago guys got in touch with OSG. OSG coordinated a debugging exercise. This led to Dave Feld from USAP to shut down one of their commercial links, which was apparently broken, and shutting down that commercial links and relying only on the second one saw the recovery, and then things were going normal again, that basically you fetched relatively quickly a large amount of the data that was accumulated, and then you slept, and then you fetched again, you slept, and that's sort of the standard pattern. So the problem was here, and the fixed one is here, and OSG organized all of the data, facilitated, in a sense, the problem resolution end-to-end. And the people in SPD3G did not have either the knowledge or the means or the understanding of how to even approach the problem and figure out what has to be done. And OSG stepped in and helped with their partners figure out what's happened and ultimately resolve it. And another example, and that I think maybe my last example, is again the international integration. What I'm showing you here is the compute time for Dune and Xenon 1 ton, and the arrows are all of the international partners. And so you can see both of these benefit from the international partners in significant ways, and OSG does all the integration. And a lot of these are international partners that already are working with the LHC community anyway. So the integration is actually kind of trivial. It just it needs a little bit of coordination. Summary and conclusions. OSG's objective is to advance open science through distributed high throughput computing. I hope I have explained the power, what I call the ingenious parallelism of high throughput computing. OSG thinks of its science stakeholders in terms of 4 categories. We think of them in terms of 4 categories because the categories require radically different ways of working together. And that's what gives the categories. And OSG offers a diversified portfolio of services to support these different science stakeholders. And if you want to know more, engage in a technical discussion, engage in figuring out what we can do for your institution or for your project, send either me privately an email or send an email straight to help@opensciencegrid.org. And you're welcome to reference this talk when you contact them directly so that internally we can figure out how this engagement was done. Thank you very much.
That's fantastic, Frank. Thank you. So I'd like to ask folks who are out there, if they have any questions, please do feel free to speak up. So I have one more, which is the thing that you described about the satellite downlink issue. That is not the first time I've heard of there being problems from a satellite downlink location and getting data to wherever the data needs to be. I think it'd be interesting for the R&E community to maybe work with some of the satellite providers and see what see if we can get peering with the science network infrastructure. Whether that be one of the local exchange points or ESNet or Internet 2 or something to help with these sorts of things. I don't know how possible that is, but it's just something that occurred to me.
Yeah, and we of course, this is such a fun example that we of course send it to Kevin Thompson at the NSF, because Kevin, or the NSF at least, sits at both ends of this, right? The NSF is responsible for the Arctic, research program, and it therefore has a vested interest in USAP, and the NSF supports the research and education networking, right? And so it's kind of absurd at some level that USAP does not have a link to the research and education network and depends on a commercial link instead.
Well, so I mean, they're sitting in Denver, right? I mean, the obvious thing would be for them to pull a circuit into the front range gigapop.
Exactly, and we've mentioned that I've not been personally involved in this specific issue, but I think it would be an obvious thing to do to just get USAP connected better into the research and education network, and it would probably even save the money, for all I know. And I think this is something that is above my pay grade at some level, but it's an obvious thing for USAP to do. And if you want to work the issue, I can try to get you in touch with. We can start in a three-way with the Chicago people, SPD3G, and maybe via them. Presumably, IceCube has the same issues, right? They must come in by the same satellite.
Yeah, my guess is that this would potentially cover a lot of people. So yeah, let's see if we can just get a brainstorming conversation together.
Yeah, and because it's an obvious one.
Yep, totally agree. Awesome. Other questions? Okay. Thank you all very much, and thank you, Frank, again for an excellent talk. I am afraid I don't have the schedule handy in front of me, but we will hear from Jason soon, I'm sure. So thanks very much, everyone, and have a wonderful weekend.
Thank you. Bye.